All right, today we're going to talk about section 2.2, which is more about graphs and displays. So this first part is talking about graphing quantitative data. And so the first type of graph is called a stem and leaf graph. And this basically shows your data in a different way, where the first digit of your number is called the stem, and then the second digit is called the leaf. So the number 26 in this case is 2, 6. Again, this is the stem, and these are the leaves. So when we construct this stem and leaf graph, it's not hard at all to construct, and it basically just gives you a quick look at your data. So in this case, it says that the data in the chart is the number of text messages sent. You do have to order the data, so we have to make sure that it is ordered. So if we look at the stems would be the first digit. So the smallest number in this case would be 16. The largest number in this case is 149. So we're going to start our stems at 1 and go all the way down to 14. So now when we put these in, it is nice if you put them in order. So if you look at the way this is written, it's easy to see 21, 25, 25, 26, 27, 28. So it's much easier if your data is ordered. So as we go through this, we'll try to get it so that it's ordered. The first number is 16. So again, the stem is 1, the leaf is 16. The next smallest number is 19. So we have a 1 and then a 9. The next number is 20. And so I'm going to do 2, 0. And then we have 23. And then 24. And then 26. And when we get to 26, 26 occurs twice. So as we list 26, we are going to write 20. We're going to write 6 twice. So 26 and we had 2 26s. Yep, there it is, 26. Then the next number, after again it's both 26s, the next number would be 28. And 28 is right here. And then I have 4 29s. 1, 2, 3, 4. So I'll continue in this way until I get all of the data listed. So the next ones, again, just for the sake of time, we have 2 30s, we have a 32, we have 2 33s. Actually, we have 4 33s. We have a 34, a 38, and a 39. For 40s, we have 0, 1, 1, so 40, 41 twice, 43, 48, and 49. I am leaving a little bit of a gap between the numbers here so that they can be easily distinguished. Again, as long as you know what you're trying to accomplish, then just leaving a little bit of space should work for your display. So our next number would be 52, then 53, 56, and 58. And we have 66, 67, 69. For the 70 group, we have 72, 76, 76, 76, and 78. For the 80 group, we have 80 twice. We have 86 and 89. For the 9-minute or 90s group, we only have 1 at 99. 10, we have 102. 11, we have 115. 12, we have 122. There are none in the 130s, so you don't have to list anything. And in the 140s, we have 149. You should also write what your key is. And so in this case, we want the key to tell us that 10/2 equals 102, so that people are aware of what your key is. Again, this is text messages sent in one day. I think this data might be a little old, but that's okay. So what can you do? How can you describe this data? What can you tell from this data? So in looking at it, these two groups are the largest two. Of course, these numbers here are the smallest, or have the least number of data points. They're not the smallest numbers, but have the least amount of data. So you could say several things, and it might be something like most people sent less than 90 or less than 99 text messages. So most people sent less than 99 text messages. You could also say, you could also say that most people sent between, and again, depending on how you want to look at this, but it's really easy to say, probably, even between 20 and 39. If you want to get a little bit more specific, you could say between 20 and 49, or between 20 and 69, depending on how you want to break up the data. So again, you have to just sort of look at it, and it is a little subjective. So again, when you're doing homework, look for the answers. Really be careful when you read what the answers are so that you can interpret the data the way you want to. That's one thing about statistics. Depending on how you interpret the data, you can get an entirely different answer just in your interpretation than someone else. Next, quantitative plot is called a dot plot. Basically, this is very similar to a stem and leaf. And instead, you're going to list all of your numbers across the x-axis. So the smallest number here was 20. Or on the scale here is 20. The largest is 45. In my data, the smallest one is 21. The largest one is 45. So we're going to go across, and then you're just going to put a dot where every number lies. So if I'm looking at this data without a whole lot of understanding of what the data represents, it looks like they should have the number 36 done twice. And in fact, we do have two number 36s. So it's again just a really quick way to take a look at your data. One other thing about your stem and leaf, if you have a lot of data in the 20s and you have so much so that your data just feels like it's going on forever, you can split the data into two pieces. So technically in this case, a different color. So in this case, you could take the number 1 and split it twice. the number 2 and split it twice, the number 3 and split it twice, and so on. So like you would think, anything between, or anything less between 0, so 20 and 25, or 20 and 24, or 10. So there wouldn't be anything for the first group of ones, but for the next one we would have 16 and then 19. For the next group, if we split the 20s, again, 0 to 4 is 5 digits. So then we would have 20, 23, 24. Then I could put the 26, 26, 28, 29, 29, 29, 29 into a separate column. Similarly, for the 30s, we could do 0, 30, 30, 20, 32, 33, 33, 33, 33, 34, then jump down to the next one and do 38 and 39. And that just allows you to split your data so that it doesn't extend so far here on your leaf. It's not necessary, but you'll see data both ways. All right, so back to the dot plot. So let's construct a dot plot for this next information. So again, we're looking at the cell phone data. So we concluded in the cell phone data that the smallest number was 16, the largest number was 149. I am not going to do the entire plot, because if we did the entire plot, we would start here at 16, and I would have to go all the way to 149. And again, for the sake of space on my picture, I really don't have the room for that. So I'm just going to demonstrate the first, let's say 40 or 50 pieces of data, or 40 or 50 numbers. So 16, 18, 20, 22, 24, 26, 28, 32, 34, 36, 38. Let's end at 40. So of course, each one of these would also have a hash mark in between those for the odd numbers. And if I look at my data, again, the smallest number is 16. So I would have one dot above 16. The next one is 19, so I have a dot above 19. Then I have 20. Then I have 23, 24, 26 twice. So I'm going to put 2 dots. 28. 29 is 4 times. 30 is 2. There are no 31. 32 has 1. Appears once in my list. 33 appears 4 times. So again, 4 dots. 34 appears once. And then we jump all the way to 38 and 39. And we'll stop there. So again, it's the beginning data, but it's not everything, just because there's not a lot of room to expand it out to 149. And that would be a definite disadvantage of using the dot plot. And if your numbers extend pretty far down the number line, that's going to get harder and harder. We could, of course, rescale this. So we could start at 15 and have a hash mark every 5, but then it gets harder to read your numbers as they go up the ladder. So some advantages one way, in both cases. All right, so conclusion. Well, it's a little harder to tell the conclusions about this data because it's sort of a partial set. So we can't really make a whole lot of inferences about the entire cell phone usage, but we can say things like the largest number of text messages sent So 29 and 33. Again, not necessarily overly informational, but because we're only using a partial set of data, there's not a whole lot we can conclude about it. We could say in this case that the majority of it was between, say, 26 and 34. So if we're looking at the majority of it, we could say the majority of the data was, say, between 26 and 33. So there's a couple of things you could draw conclusions about, but when you're only using a piece of the data, it's not a good idea to draw conclusions. All right. The next one then is to graph qualitative data. And the way you see a lot of qualitative data is done with a pie chart. So pie charts are a little different because when you look at the number, so in this example, we have the associates, bachelor's, master's, and doctoral degrees, and then the number in the thousands that were conferred is set in 2014. And so when you look at that, we have to decide how much that is as it is represented in a circle. So there's several things that we have to add to this chart. So we are going to add a couple of columns. The first thing we're going to add is the relative frequency. And then the second thing we're going to add is the angle measure. So we're going to have to think back to geometry a little bit. Full from the top of the circle all the way around to the rest of the circle is 360 degrees. And so as we figure out our percentages, if I'm looking at this piece of the puzzle in gold, if I were to draw the line right here, this portion would be about 180 degrees. So I have a little bit more. And this portion that's 180 degrees also would represent about 50% of my data. Now that's just looking at this part of the gold. So if we included all of the gold, we would have to have more than 180 degrees and more than 50% of the data. And that's what the relative frequency and the angle measure is going to tell us, exactly what these numbers represent. So it's not quite as intuitive as some of the others that we've done. There's a little bit more work you have to do on this. So if I'm going to do relative frequency, remembering that relative frequency takes your frequency and divides it by the number, total number in your sample set. So the first thing then we have to do is sum up all of these numbers. So if I add all of the degrees together, then that sum is going to be 3,805. So the first relative frequency for associate's degrees would be 1,003 divided by 3,805. So if I get my calculator out, I have 1,003 divided by 3,805, and my relative frequency is 0.26. Well, if we're looking at 0.26, then that's going to be about a fourth of the circle. It's about a fourth of the circle. So we have to look at it several ways. To find that angle measure, I'm going to take my relative frequency and I'm going to multiply it by 360. So I'll take the angle measure. I'm going to multiply it by 360 because this is the percent of the whole circle, and that'll be about 95 degrees. So the angle measure is at about 95 degrees. If I do the same thing for the bachelor's degree, I have 1,870 divided by 3805, which is about 49% of the data, or about half of the data. If I multiply that again by the 360, hopefully you realize it should be at about 180 degrees. So in all these cases, we are going to round. So this is about 0.49, which is about 177 degrees. For the masters, if we do it the same way, we get about 0.198, about 20%, or 71 degrees. And for the last one, 178 is 0.047, which is about 17 degrees. So when I draw my circle, look for the things that make sense to you. So this one is about half the circle, 180 degrees. No one's going to get a compass out and make sure that you're measuring exactly 180 degrees. But I can say that this portion right in here represents my, now be careful, bachelor's degrees. From there, I also know the next easy one is the associate's degrees, because the associate degrees are about a fourth of the circle, or 95 degrees. So if I look at what's left of my circle and I cut it in half, this piece right here will represent the associate degrees. So that leaves me about 71 and 17 degrees. If I add those two up, that's 88 degrees. So again, that's about a fourth of the circle. So that should make sense because that's what I have left. 71 degrees, well, this right here we know is 90 degrees. 90 times 4, because you're going to go all the way around, is the 360. And so if we have 71 degrees versus 17 degrees, then again, change colors. So now we'll have, and again, you can just estimate it. That actually might even be a little bit pink. But that's why you're going to label it. So this one is the doctoral. And then the last one would be the masters. So a couple of things you have to do a little bit more work here. Just remembering that it's 360 degrees all the way around. Halfway around would be 180 degrees. A fourth of the way would be 90 degrees. And then just kind of whittle the rest of it. No one's going to get a compass, but you should be able to tell the main ones. And just to help clear up, also, a lot of times these are colored. So you'll see these on all different colors, similar to the one above it where it's colored. You also will see the percentages marked. So in this case, the master's was 19.8%. So you'll see 19.8%. And oftentimes it is a percent, not a decimal. The decimal doesn't mean anything, but people can understand 19.8% of the population got a master's degree. So if I do the same with the bachelor's degree, this is going to be about 49%. The associate's degree is going to be about 26%. and then the doctoral at about 20%. Oh, no, sorry, about 5%. So my doctoral group is probably a little bigger than it should be, but that's okay. The next type of chart, conclusions. We did not answer any conclusions about this, right? Well, there's several things you can talk about. You can say the bachelor's degree represents the most degrees earned. You can say that the bachelor's degree is about twice what the associate's degrees are, or the bachelor's degree is about twice what a master's. So maybe we say twice as many received bachelor's degrees than master's and doctorates combined. So a lot of times there is data that you can look at and make interpretations that are different than what somebody else interprets the results as. And it's okay as long as it is a legitimate interpretation. All right, next one is a Pareto chart. It's a vertical lines that represent the relative frequency or the frequency. They're positioned from decreasing. So that's the biggest thing here, is that the largest goes down to the smallest. So it's the largest to the smallest. We're still talking frequency, and we're still having categories. It's from largest to smallest. Where a histogram represented all of the information, and you could see the difference in the height of the histogram bars as they are relative to the data. This one, because again it is qualitative, there's no numbers, or there's no category, they're more categorical. So it's going to be a little harder to give us numbers to these. So this says, in 2014, these are the leading causes of death in the United States: accidents, cancers, chronic respiratory disease, heart disease, and stroke. So what they want you to do is graph this information, again, so that people can see what's the leading cause, what kills most people versus what kills least people. And so if we set up our table, along the x-axis now again is going to be the categories. Along the y-axis is going to be, in this case, this is the number of deaths. And you really should say that it is in thousands, because I'm not going to be able to put all of these numbers on the chart. So I am going to have to make sure that I am positioning out my numbers so that they make sense. So the largest one would be the heart disease. So that's 614,000. The smallest is a stroke at 133. So my scale on the y-axis has to go to at least 600,000. It's going to start, the lowest would be 133,000, so that everything is not just squashed in the bottom of the chart. If I go by 70s, that's 7, 440, 210. Actually, I'm going to run out of space. Hang on. So let's make this one 140, 280, 420, 560, and then 700. So my first bar has to go all the way up to 614,000. So you're going to just have to estimate. I'm going to put about 614,000 here. This is heart disease. Next one is cancer at right about 600,000. So it's not a whole lot less. Than heart disease. So this one would be my cancer box. The next one drops pretty significantly down to 140,000 from 147,001. So it's going to drop pretty significantly. And this is going to represent chronic. Respiratory disease. Then the next two, again, are still way down low, so it's going to be a little harder to decipher because of the way that this is scaled. So this one was 147,000. This next one is going to be accidents. And the accidents represent about 136,000. And then the last one is about 133,000. And that's going to represent strokes. So again, as you're looking through this, largest to smallest, so you can see again, it's a really quick visual of which is the leading cause of death in the United States. It's also a little easier to maybe draw conclusions now because it's a whole lot of, you can look at a lot of the difference in the heights in this case. This one, you can say heart disease and cancer contribute to, nearly 3 times what everything else does. You can say that more people die of heart disease, more people die of heart disease and cancer than all other deaths. Truthfully, more people die of the heart disease than everything else combined, just about. Well, cancer is 3 times as long. So there's a lot of conclusions that you can draw here. And so you can say things like heart disease is, or contributes, probably a better word, to 3, let's just say more than 3 times what, more than 3 times, I guess we should say, deaths. The number of deaths than chronic respiratory accidents and stroke combined. Of course, the same data could be said if you just replace the words heart disease with cancer, because it's still a true statement. Also, as always, and I don't think we put one even on our other chart, but you really should have always a label. So this is the top 5 causes of deaths in the U.S. Likewise, on my pie chart, I should also have, I can put degrees earned for that title. So you should always have a title on the chart. And because these last 3 are squished really close together, had we had a little better scale on my chart, those would have been easier to see as well. If you're making sure that when you're presenting material, that the presentation looks right, that the groups look right. And that's why you're going to want to use Excel, or you're going to want to use some sort of a program to make sure that everything looks more proportional than just by hand does. And that is called a Pareto chart. Right? The next one we're going to talk about is graphing paired data sets. So a paired data set is going to have two values, similar to an X and a Y coordinate system. So it's going to look like an XY coordinate system that you did in algebra. They're ordered pairs that you're going to put on a coordinate plane. And it usually then is used to show the relationship between two quantitative variables. So our example says a British statistician introduced a famous data set called Fisher's Iris data set. The data set described various physical characteristics such as petal length and petal width in millimeters for 3 species of iris, the petal lengths from the first data set and the petal widths from the second data set. As the petal length increases, what tends to happen to them? So again, they're plotting each point that compares petal length to petal width. Petal length to petal width. And as they do that, then you can see that as the length increases, so does the width. So as the length increases, so does the width. Or the width also increases. All right, time series data sets. It's composed of quantitative entries taken at regular intervals over a period of time. So again, time series. As time develops, what happens? And so a lot of times you will see this when we're talking about years. So we can compare data as it increases or decreases over years or over time. So this example in the table lists the number of motor vehicle thefts in millions and burglaries in millions in the United States for the years 2005 to 2015. Construct a time series chart for the number of motor vehicle thefts. So we're going to do just motor vehicle thefts this time. So let's make our chart. This is going to be thefts. And again, we need to make sure that we tell them that this is in millions. Then across the x-axis, we're going to have, we will have a break in the graph because we're not starting at year 0. We'll start at 2005. We're going to end with 2015. Again, there will be other hash marks in here. So 2005, this would be 2007, 2009, 2008. The other ones, so this would be 2011, 2012, 2013, and 2014. And then our thefts in millions, the lowest number of thefts look to be about this 0.69. The largest number is 1.29. So I want to make sure again that I don't start so close to the bottom that I have a flat curve, or a flat line in this case. So if I go 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, and 1.4. So this would be, again, number of thefts per year. And in 2005, we had 1.24 million. In 2006, we had 1.2 million. In 2007, we had 1.1 million. In 2008, we had 0.96, almost 1. In 2009, we had 0.8. In 2010, we had 0.74. In 2011, we were at 0.72, so it's going to be really close. 0.72 again, 0.70, 0.69, and 0.71 goes up just a little bit. So basically, whoops, connect the dots a little better. It's really important to you that you get all of your proportions exact. I do recommend you using graph paper for some of this. If it doesn't bother you as badly, then it's fine. But obviously this would look a lot neater if I actually had a graph paper or if I actually put it on an Excel program. So the conclusions here, it looks like they dropped pretty good from 2005 to probably about 2011, and then they started leveling off. So thefts decreased from 2005 to probably around 2011, and then remained steady. It did have a slight rise in 2015 from 2014, so if your conclusion, you can certainly say that as well. You know, they decreased until 2015, where they increased for the first time. So there's a lot of, again, conclusions you can draw based on the data. And that will wrap up section 2.2.